All right, I am
Recording.
Scott Kirk. I am your host today for the second. Okay, I am Scott Kirk, and I am the host for the second presentation of 5 for the SRR Summer Internship Lecture Series. Last week, we were honored to have Dr. John Teal give his presentations on 4 years of risk assessments. And today we have Dr. Jonathan Cirtain from BWX Technologies, which is referred to as BWXT. I'm in Lynchburg as well, but not with Jonathan. I'm in a different office. But Jonathan's online with us today. And so I'm going to introduce Jonathan before we get started. So Jonathan Cirtain is a Vice President and Chief Technology Officer for BWXT. Jonathan also serves as the President of BWXT's Advanced Technology LLC, a subsidiary of BWXT, in which he oversees innovative nuclear technology applications, including engineering for NASA's nuclear thermal propulsion program, 3D printing technology for aerospace and defense applications, and radiochemical and radiopharmaceutical product development for cancer diagnosis and treatment. Dr. Cirtain spent 9 years with NASA, beginning his career as an astrophysicist, holding positions of increased responsibilities at the Marshall Space Flight Center. He concluded his tenure with the agency as the manager of the Science Research Office, overseeing a staff of nearly 170 scientists and contractors in applied science and technology development. During his time with NASA in 2010, Dr. Cirtain received the most prestigious honor given by the U.S. government to scientists and engineers in the onset of their independent research careers, the Presidential Early Career Award for Scientists and Engineers. Amongst his various honors and appointment, Dr. Cirtain has served on advisory committees for NASA, the National Science Foundation, the U.S. Department of Commerce, National Oceanic and Atmospheric Administration, the U.S. Office of Science and Technology Policy, the National Academy of Science and Engineering, and the Royal Academy of Science, the European Space Agency, and numerous universities. Jonathan earned his Ph.D. in physics from Montana State. He's also a graduate of the University of Memphis, and he holds a bachelor's degree in physics and mathematics as well. And with that, Jonathan, I'm going to turn it over to you for your presentation. But first of all, Jonathan, thank you very much for agreeing to support the lecture series. I know it means a lot for me and for SRR, but even more so to our interns. So I'm going to turn it over to you, Jonathan.
Thank you very much, Scott, and I'm really happy to be with everyone this afternoon. When Scott asked me to do this, he kind of left the aperture open on what I might talk about, but given a lot of the focus recently by NASA and other agencies within the U.S. Government for increasing the technology uses in space for propulsion and power, I thought it would be an interesting topic for me to share both my perceptions of space nuclear power and propulsion, but also kind of the rationale behind the use of nuclear reactors as power plants for propulsion systems. So I think with that, the first thing that I'd like to do is kind of introduce everyone to BWXT. So we're right at 6,700 employees. We have 13 manufacturing facilities now across North America. Generally, we're known for making the nuclear reactors for the U.S. Navy, but we also do a wide variety of different things, including fuel for the CANDU power reactors in Ottawa or in Ontario. We do a lot of services work for those Canadian deuterium reactors as well, the CANDU reactors. We've done a variety of different development work for all sorts of different programs across the entire Department of Energy and NASA government lab complexes. And as a consequence, we have a variety of different technologies under development, some of which I'll talk about today, but others are in other parts of our business, like radiopharmaceuticals for the diagnosis and treatment and predominance of cancer. So a lot of different things that we do within BWXT. And today I'm going to focus on nuclear propulsion for space exploration. So, not often do we get the opportunity to speak about this, but over the course of our history, not only have we been making nuclear reactors for the U.S. Navy for 60 years, but we have about 40 different nuclear reactor designs that we've developed over the course of that same period. Some of these were actually in submarines, like the first Rickover submarine, the USS Nautilus. But there are also a variety of other reactors, including, Scott, I don't know if you knew this, but we had 3 reactors here in Lynchburg, Virginia, the CX series that we operated at the Mount Ethos facility. We've developed designs for a variety of different reactors, both commercial and government use. And a couple of those in particular I'm going to talk about today: Space Nuclear Thermal Propulsion System, the SNTP program, SNAP 100, GMO, or the Jupiter Icy Moons, NASA's Project Prometheus reactor system. And we've done a variety of other things for reactors as well, including the manufacture of, pardon me, fuels for the Advanced Test Reactor at Idaho National Lab, or the high flux isotope reactor at Oak Ridge, things that we have as ongoing enterprises today. So I think with that, I'm going to kind of provide a brief history of what BWXT has done in terms of spaceflight systems since we really got into the business with Project Mercury, one of the first rocket launches to successfully reach space back in 1959. With Wernher von Braun in the early 60s, we started the development of the design systems for the NERVA test program and Project Rover. Those are 2 separate activities within the U.S. government, and we were a participant in both. We provided, BWXT predominantly makes big round things for nuclear reactors, and we contributed big round thing manufacturing to both the Apollo space program and also Skylab. So we've been building hardware for space for quite some time, something that's not something that we get to take full marketing value for very often. So I'm pretty excited to get to tout those experiences to you today. We've had a variety of different contracts with NASA for the design of thermal propulsion systems for space. One in 1987, another one in 2003, and then our most recent as part of the NASA Nuclear Thermal Propulsion Reactor Design Concept, which started within the Space Technology Mission Directorate at NASA as part of a game-changing development program. This is a funding opportunity within Space Technology's Mission Directorate. That's a GCD, Game Changing Development. We've been working on that since 2017, and that's an ongoing activity for us. Right now, we're making fuel for that effort, and I'll talk a little bit more about the current iteration of nuclear thermal propulsion as NASA sees it in my following slides. So, just the need for space nuclear propulsion. Pardon me. So one of the things that didn't really come out in my bio is my background in physics is really astrophysics, where I had the opportunity to study the sun and its atmosphere during my days within NASA. And something that doesn't come across that often for public consumption is that the sun actually has variability. It has its own seasons, if you will, over an 11-year cycle, where there's variability in the number of sunspots on the sun's surface. Those sunspots are representative of the magnetic field of the sun, and that magnetic field emergence actually drives what's known as space weather. So the sun's atmosphere expands and contracts over the course of this 11-year cycle. There's a variety of different energetic events that are associated with the emergence of sunspots and their evolution as a function of time. And that interchange of energy, the drivers of space weather, actually influence the solar proton environment, the high energy particles that are streaming from the sun out into the heliosphere out into the solar system as a function of time. And what you're seeing on the right-hand side is a chart of that activity. So that 11-year cycle is indicative of the sinusoid that you see. And in the upper part of the graph, the gray area, is where the solar particle event radiation detection probability is at its highest. And that time period not only is higher solar proton activity, but also the higher likelihood for solar flares and coronal mass ejections. And this is where there's a very large amount of high energy radiation, both particles and electromagnetic radiation, and oftentimes of substantial enough energy to be detrimental, if not lethal, for humans. So at the top part of the sinusoid, at the peaks, you can see in the green boxes time periods where it would be a really opportunistic time for a launch from Earth to Mars. But in some of these instances, say 2037, the probability of galactic or of solar energetic events is high. So the threat potential, the risk to human astronauts is higher during those periods. And you can see how it fluctuates for those different green and yellow boxes. At the bottom of the graph is when the solar activity is lowest, the number of sunspots is at its minimum. And so the solar atmosphere is contracted. And the consequence of that is the leakage of galactic cosmic rays into the heliosphere. And again, these are high energy particle events. Those high energy particle events are detrimental to humans. Doesn't really work that way inside the Earth's magnetosphere. So folks on the space station aren't nearly at as much risk. They're also near the equator for a fair fraction of their total orbital duration. And so the likelihood that humans in low Earth orbit on station being impacted by galactic or solar events is fairly low. But once you get outside the Earth's magnetosphere, you're no longer protected. And the consequences for Mars transportation are indicative of this plot. So one reason why it's important for us to develop something like a nuclear propulsion system is to minimize the transit time, minimize the time period when you're outside the magnetospheres of the Earth and Mars, and reduce the risk to human susceptibility to these extrasolar or solar energetic events. Another reason, probably evident from this plot, but I'll go into it in detail. Another reason for a nuclear thermal or electric propulsion system is launch windows, right? Being able to launch on the day that you like to plan. In the case of a nuclear thermal propulsion system, you might need to plan 5 or 8 years in advance, maybe even a decade in advance of the launch window, given the proximity of Mars to Earth. The launch windows are fairly narrow. If you watch the Perseverance launch, they only had a few days that they could launch that vehicle. So they really had to hit their target, be ready well in advance. They had to hope that the weather worked out. And so the launch windows are fairly narrow for these interplanetary launch opportunities. And as the window grows, the amount of propellant required also grows because of the interchange between the gravity wells between the two planets, launch opportunity, transit times, distances between the planets. All of those things increase the amount of propellant required. And at day 0 of launch, if you are actually to hit your target window, you need about twice the chemical propellant, twice the fuel for a chemical rocket versus a nuclear rocket. But as the time period past that 0-day launch window grows, there's a slow growth in fuel requirements for a nuclear rocket, but a growing geometric requirement for fuel for a chemical rocket. And you can see at about day 50, day 60, it really starts to become a fairly rapid growth in chemical required versus chemical fuel required versus nuclear fuel required. So again, another rationale for having a nuclear propulsion system is the expanse in launch window opportunity that advanced rocket system affords you. Another reason for that is safety, abort, the ability to turn around if things don't go well. Most incidents occur during ascent, during the first phases of operation of the system. And it'd be really great if in the event something went wrong, you could turn around. But for a chemical system, you have about 5 days, 5 days out of 210 that you can call do-over and turn around and go back to Earth. But for an NTP system, you're roughly halfway into the transit where you can still turn around and safely make your way back to Earth. There are a variety of different reasons why you might need to abort. Maybe the two crew members just don't get along well. The likelihood of that's probably low, but other things like damage to the spacecraft because of debris events or ECLS impacts, ECLS being the environmental and life support systems on board the spacecraft. For a variety of different reasons, you might have an issue with life support systems and need to turn around, and the consequences of all of those activities, all of those rationales for turning around are pretty deleterious for such a long duration mission. And so having the opportunity to abort is pretty important. So a much more substantial abort capability with nuclear thermal propulsion. Then the last thing to point out before talking specifically about the technology is the two classes of missions. So a conjunction class mission, shown on the left, is really where, say you take off September 1st of 2037 on day 0, about 210 days later, you will have caught up and slowed down to Mars. In this conjunction orbit, Mars is pretty close to the Earth when you take off, and you just have to catch up with it on your transit to. But the consequences of a conjunction orbit, it's called a minimum energy orbit. The consequences are you got to stay for a while at Mars once you get there. So 496 days, a little bit more than 1.25 years are of time on planet are required to get back to Earth. You can see that Earth return Mars departure date of September 8 of 2039. You've now been on the planet for a year and change, and you're going to slow yourself down, spiral your way into the Earth from the moon. So just slowing yourself down in terms of your relative location to the sun. So that's a conjunction orbit, minimum energy orbit. The other type of mission class is an opposition class. So this is where Mars is quite, near opposition relative to the sun from Earth, and you take off from Earth, and about 217 days later, so a little bit longer in transit time, but it requires more energy to accelerate the spacecraft to make it, to catch up to Mars in this instance. But the benefit to that is a much shorter stay, 30-day stay on Mars, and then you spiral your way back into an Earth return orbit 30 days later. And so the total duration of an opposition class mission is 650 days versus the 916 days of a total mission for a conjunction class, with a lot of things held constant. The amount of fuel used, the type of propulsion system, the amount of thrust that the engines have, those kinds of things held constant. That's what is being used to give you these two mission concepts, the architectures for these things. But there's consequences there are consequences for either of these mission classes, and those have to be taken into account when designing the architecture for the vehicle or for the stay. And so that's worth spending just a moment or two of time on. Now, the minimum energy orbit on the left might get you there with the least amount of fuel and maybe a less massive overall spacecraft. But having to stay on planet for 1.5 years is going to require a number of cargo missions, maybe greater than 10 is currently under study. 10 different cargo missions to deliver sufficient payload volume to planet to make sure that the astronauts during that 1.25 years have enough resources, habitation, oxygen, food, heat, energy, et cetera, that they would require for such a long stay. The amount of material that you would need for a 30-day stay, the opposition class, is going to be a lot less. It's still going to be significant. 30 days is non-trivial. Even for the Apollo missions, where they only stayed a few days on planet, they still had to land tens of tons of content on the moon. So there's still going to be a significant amount of cargo that has to be delivered to Mars for a 30-day stay. And the vehicle is going to weigh a bit more because it has to carry more fuel so that it can burn the engine longer and accelerate for a longer period of time to a higher terminal velocity to catch Mars for the opposition class transit. All of those things have consequences. They all factor into the engineering and the trades that go into the design of those rockets. And I'm going to talk a bit about that for the balance of my time. So I've spoken a bit about why thermal nuclear propulsion, and I've itemized those things on the first subtended bullets there. But BWXT's role is a different aspect of this that I want to talk about a little bit. So we've been working with NASA since 2017 on the latest iteration of this engine design. I'll speak to it in a couple of different ways in a moment. On top of just the reactor concept development, we've also been looking at licensing support. So what would be necessary for licensing the manufacturing of the fuel, what's required to launch a nuclear reactor system from Cape Canaveral, what's necessary for a ground test. If we were going to test this rocket either at the Stennis Space Flight Center in Mississippi or out in Idaho at the Idaho National Lab. In either of those instances, a license would be required to operate that reactor for those ground tests. We've been working on fuel and core fabrication development. If you're looking at this image on the right, the core is the central cylinder that's between the two black dots, if you will, at the top of the bars that extend from the aft skirt toward the top. It's kind of got the cutaway that you can see the wedge cut out of that cylinder. That's the reactor core. That reactor core with all the vertical lines running along the length there is full of fuel elements. That fuel meat is a particular type of material, and then it's surrounded by cladding, a different type of metal that actually encases that fuel meat to make sure that the fuel's not moving around inside the reactor core, because while it doesn't necessarily matter that much if some of the reactor, the reactivity, the nuclear inventory, the types of radioisotopes created during the fission events, while you're not so much worried about those getting out of the reactor core because it's in space and there's lots of nasty stuff around and it's a vacuum and all that other kind of stuff, you still want the fuel located where the fuel needs to be located so that the neutronic performance of the reactor meets the expectations of its design. You don't want the uranium-235 moving around to locations where it shouldn't be, so the reactivity is more or less controlled because you keep it in place with the cladding. So there's rationale for how we actually build that reactor core. And so that's required a lot of materials development, both for the fuel and for that cladding, the core fabrication development. We've been manufacturing in refractory metals since 2017 to demonstrate the ability to maintain structural integrity, both for the fuel and for the overall reactor core. And then we've been having to demonstrate that that would work with high assay, low enriched uranium, HALEU fuel, less than 20% enrichment. So I'm going to go into that in a bit more detail. So just in terms of how the reactor works, so you have coolant. I'll go back a slide. The coolant is actually above the shield. So the shield is this disc at the top of the reactor, and you can see an inlet just to the right of the reactor shield. And that inlet is connected to a large tank of hydrogen, cryogenic hydrogen liquid. That comes in through this coolant lane and is pumped into an inlet plenum that you can see in the center of this box here, which then drives the reactor, drives that hydrogen through the moderator elements in the reactor core or through the nozzle and into the radial reflector, so the outer sheath of the reactor. You need to both maintain temperature integrity on the outside of the reactor, but also internal to the reactor. So you're driving that hydrogen coolant outside the reactor core and in through the reactor core. And as the reactor transfers thermal energy from the fission events, from the heat created during the nuclear reactions, that heat is dissipated by that fluid flowing both through the outer reflector, but also through the moderator and the internal reflector, the inlet manifold, through the fuel elements. So you can see it being pumped down through the reactor core itself. It exits the outlet, the reactor core. Going back again a slide, it exits the reactor core and is pushed through this nozzle. So the pressure differential from the above the nozzle to inside the aft skirt creates substantial increases in thrust. And so you get a high thrust, high velocity exhaust gas pushed out through that nozzle throat, through that neck in the engine. And so that's essentially, in a nutshell, how a nuclear reactor creates thrust. Generally speaking, it's heating hydrogen gas from 19.7 Kelvin to somewhere north of 2500 Kelvin. You can think about the power of a reactor, the amount of thrust the reactor can create, being proportional to the diameter, the power of the reactor. So number of megawatts in the reactor core is directly proportional to the amount of thrust, to the numbers of pounds of thrust that the reactor can provide. The ISP, the fuel efficiency of the reactor is directly proportional to the temperature of the expelled propellant. So as the temperature goes up, the fuel efficiency goes up, the ISP goes up. So the higher the ISP, the more fuel efficient you are, the higher the thrust, the more power you can deliver to accelerate the spacecraft. Those two things in combination are one of the real benefits to a nuclear reactor. The designs that we've been working on are north of 150 megawatts, even as high as 500 megawatts for the reactor core. That gets you somewhere between 35,000 and up to 75,000 pounds of thrust, depending on the configuration of the engine. And then the designs call for in excess of 2,700 Kelvin for the expellant temperature of the propellant. And so that gets you fuel efficiencies or ISPs north of 900 seconds. So very efficient systems. And just for comparison, the main shuttle engine for the space shuttle had about 450 seconds of ISP. So about half that, half as fuel efficient as a nuclear thermal propulsion system, but about 1 million pounds of thrust. So substantial amount of thrust capacity for a shuttle main engine. Only burned for about 4 minutes, where a nuclear thermal propulsion system can burn for about 12 minutes for the same amount of propellant stored. So there's a lot that goes into the design of a reactor, and just going through a little bit of that, you can see the overall design on the left and the different types of physics that need to go into that reactor design. There's thermal hydraulics, exactly how does fluid flow and how is it heated as it's transferred through the different channels of the reactor core. What does the neutron profile look like inside the reactor core? How many fission events are you creating as a function of position, both in diameter and length of the reactor? And how does that reactivity, how does that heat impact the structural mechanics of the system? Are you getting expansion of the reactor core? Are you getting cracking of the materials? What are the various implications associated with both the transfer of heat into the fluid, the thermal hydraulics, or the creation of heat through the fission events, the neutron physics? And how do you maintain reactivity as a function of time, as a function of burn rate? And that's all done, in this case, with control drums, reflectors. Those are the discs in the yellow annulus that surround the core. You're actually rotating those to change the neutron reflectivity at the outer diameter of the reactor to make sure that you're keeping the neutron flux the K effective at the right level to maintain reactor control. And then having figured those things and a variety of other thermomechanical stress and material characteristics out, how does that all fit into a system analysis, enforce your design and drive other things like the types of fuels that you would use? And so those types of fuels are shown in the a couple of different ideas are shown in this bottom right-hand panel. What we've been looking at is how to make the fuel meet. What's the right way to get densified uranium fuel kernels created? Generally speaking, what you want to do is take some sort of molecule of uranium, whether that's uranium dioxide, uranium nitride, uranium carbide, something that binds the uranium up in a structural environment. Sometimes you want to coat those so that you actually have coated those kernels with a candy-coated shell to keep the reactivity, the nuclear inventory, the radioisotopes contained within that shell. That's trisotopic fuel or other types of carbide fuels. Maybe you use a fuel meat. Maybe you press them into bars and create a ceramic fuel. Whatever the case may be, there are a variety of different fuels that you can use and how you coat those, and then how you characterize those coatings both thermomechanically and their ability to maintain the stresses of the nuclear inventory that builds up during the fission events. So whether you're using molybdenum or tungsten as those coatings, or whether you're putting them into a fuel element like you're seeing in the bottom right-hand figure with the fuel bars pushed into or running through molybdenum canisters that contain the fuel elements. A variety of different tests are ongoing right now to figure out what the optimum design for the fuel is, and then that feeds back into the design of the reactor core. To make any of these things, you have to figure out the right way to join various materials. So in the kind of the bottom center, that blue image, you're actually looking at the welding development in an argon bath of a molybdenum fuel cartridge. That little honeycomb looking thing in the center of the image is actually molybdenum, and we're welding a lot of little molybdenum cylinders. Each of those holes is actually a cylinder of molybdenum, a rod of molybdenum that's being welded into place inside that honeycomb shape, so that you've got those integrated fuel elements that you see in the bottom right-hand corner. And then a variety of different applications for data science and artificial intelligence are being used to assess the characteristics of 3D printed versions of these fuel elements. And you see a Hastelloy X alloy 3D printed fuel element concept in the bottom left-hand image there. And that image, the ghost-looking image that sits to its right, is actually an as-built collection of data. While that part was being printed, data was being collected to look for defect in the as-printed part. So using these types of techniques and unsupervised learning algorithms to determine the efficacy of the built part, determine if it has defects, cracks, fissures, etc. A lot of different techniques are being developed to support advanced manufacturing techniques for both welding and joining and the use of new technologies like 3D printing. So just more on fuel. Like I said previously, the ISP is directly proportional to the exit temperature of the fuel, the max fuel temperature. And so a variety of different fuels are being looked at because of their performance in both temperature, how high you can operate those, but also exposure to hydrogen. Because some of these things don't do all that well when exposed to hydrogen over time. And so you can get hydrogen infiltration into the material, which then causes some of the constituent materials inside those fuels to make their way out. And that's not necessarily good. It's also more often than not bad. So you want to make sure that you can make things that don't break down either at temperature or when in the presence of a hydrogen environment. So a lot of tests are ongoing here Those different fuels will make up fuel elements. So the combination of the fuel meat and the material that it's packaged within, those then make up fuel assemblies. The fuel assembly is kind of that whole cylinder in the gray there. And then you add those fuel assemblies up into a moderator block. So each one of those little small dark circles is a fuel assembly that's all situated inside a larger moderator block. The moderator block is an interesting material. Given that it's high assay LEU, you really want to make sure that you get the right amount of energy transfer from the neutrons into the reactor core. You slow the neutron, you change the neutron spectrum so that you minimize the number of fast neutrons and maximize the number of thermal neutrons so that you have a thermalized reactor core, getting the most energy transfer out of the neutrons into the reactor core, and then from the reactor core into the coolant, the hydrogen. So that's kind of the overall schema that we're showing you there, from fuel creation in the upper left or across the top of the chart to the fuel elements, the fuel assembly, the moderator block, and then the overall reactor subsystem, the reactor core itself. So once you've got a design, you have to figure out how to maximize a variety of different parameters. A lot of that design margin goes into the moderator material. Is it a zirc hydride? Is it a yttrium hydride? Is it some other material? What you make the reflector out of? Is it beryllium? Is it B4C that you use as a poison? How do you manufacture the control drums? These are all different parameters that you have to consistently match with a variety of the different options that you have in the design process. Once you've decided on a fuel, then that fuel is going to inform the cladding material that you would use. The cladding material has to interact with the moderator and the coolant. So a lot of different things factor into the overall design. And once you start making some of these decisions, there's a pretty comprehensive test program that you have to go through that's going to demonstrate the efficacy of the material choice, but also the manufacturing choices. Can you manufacture welds that don't crack in these environments? And do you have stress relief processes that can make those welds strong and not brittle? So a variety of different things have to be tested along the way, and that's the intent of this slide. And really what we've been doing with NASA since we started the early R&D that we began back in 2017. So what you're seeing in the bottom left-hand corner here is a variety of different welding developments that we had, from laser welding to a variety of other types of weld, but also the characterization of those welds. So in the bottom left panel, but in the upper right image, you're actually seeing the characteristics of the weld that was created during the laser weld and the material implications that it had. We've done this in such ways that we've created welds that have this type of geometry, but also the grain boundary, kind of that interface between the lighter gray and the kind of shinier part where the weld is. So you've got the actual weld running through here, and then just the wrought metal out there. And the interface between those two is a area where a lot of failure, cracking can occur. So you can get crack through the weld. You can get crack at the interface between the wrought material and the weld. And so we've been doing a lot of different characterization on these types of welds, both using non-destructive engineering techniques, ultrasonic, X-ray, CAT scan, 3D tomographic imaging, but also destructive engineering, cutting these things up and putting them under a microscope and really interrogating the quality of the weld, both in depth and cross-section, to understand what they look like, both just having been welded, but then after putting them through a series of different tests in a relevant environment, in a hydrogen bath, heating them up to temperature, cycling the heating of them, et cetera, and making sure we really understand the character and nature of those welds. Once we get it kind of to the point of satisfaction where we think things are going to work well at this low R&D, low technical readiness level, we kind of migrate. Well, we don't kind of. We migrate those through a series of different tests to make larger versions of these things at the lab scale. Maybe take these non-nuclear components in the bottom left here, fill them up with natural uranium and natural uranium that's undergone the right fuel manufacturing paradigm for the eventual fuel meat, and heat those up and see what the implications are between interaction between the uranium and the fuel element. Make sure that we understand that process, and then scale that up to eventually manufacture them at scale. Inside a large manufacturing facility with the proper licenses and capabilities to manufacture reactor systems. So on the, wow, this didn't pop up before, but when we're doing the pilot scale, we're doing kind of at the fuel element level, and then we integrate those fuel elements into a fuel assembly. So on the upper right in that panel, the cylinder within a cylinder there is an actual fuel element, inner and outer fuel element for the HIFER reactor at Oak Ridge National Lab. So that's uranium fuel there that's clad in aluminum. And those bars that you're seeing to the right are various different fuel elements. Actually, the thing on the left is called a fuel assembly, and the things on the right are all fuel elements. Those fuel elements go to a variety of different research test reactors across the United States and in Europe. And fuel elements are integrated together into assemblies. And so once you've taken them through early R&D, non-nuclear tests, up to a pilot scale, up to the fuel element scale in the center, and then on to the assembly scale, there's a variety of different tests, both for manufacturing, but also demonstration of the quality of the design that are required to get to the final fuel assemblies that are used in operating reactor systems. Throughout the course of last year, the National Academy of Science and Engineering carried out a study on behalf of NASA to look at what would be necessary to use nuclear thermal propulsion to support both cargo and human missions to Mars. I had the distinct honor of participating in that study as part of the Academy, and this is from Chapter 2 of the Academy's report that outlines the Academy's recommendations for the timeline for the development, deployment, operation of reactor systems for a nuclear thermal propulsion spacecraft. As you can see in the upper left, we believe that it's necessary to first demonstrate cryogenic fluid storage and transfer. Can you put 10,000 kilograms, 10,000 liters, of hydrogen at 19.7 at 20 Kelvin, maintain it for a month, let's say, and then open valves, operate that cryogenic fluid management system with the necessary controls and the lack of leakage for hydrogen, so that you could demonstrate that you'd be able to launch one of these systems with the fuel, assemble the spacecraft in space, too large to assemble on the ground, so you'd have to assemble it in orbit. So you got to launch with the fuel separate from the spacecraft, as an example. So do you have the proper storage capabilities to store hydrogen on orbit? And then at the same time you're doing that flight demonstration for cryogenic fluid storage and transfer, build up a prototype of the propulsion system, take it to preliminary design review, PDR, through critical design review or final design, CDR, build the prototype up, and execute a number of tests. The Academy recommended that it was probably good to go ahead and invest in the necessary infrastructure on the ground to test that prototype on the ground. But you can see that there's a lot of preceding activities necessary to actually get to that nuclear ground test, including component tests, reactor fuel moderator control systems, separate effects testing on all of that, integrated tests on all of that, to make sure that the systems work both at the fuel meat level and all the way up through the assembly level, the integrated component level for the reactor core with the reactivity control systems, and then finally in an integrated ground test. Once you've got that ground test, you don't have a lot of time, maybe about 9 months per this schedule, before you would start moving to a cargo mission development. So while the ground tests are going on down there in the bottom center, you're actually developing the first flight system and taking it through PDR, CDR on its way to a launch in 2033. Remember, you've got to take a lot of equipment with you to Mars, land it, make sure that it's landed and safe and operable before you ever send humans out there. So at least one large cargo mission, if not multiple cargo missions, would be required. They need to start in 2033 for a minimum energy transfer. Maybe you could get another one off in 2035, maybe another one off in 2037 if you were going to do a 2039 human mission. And so you can see that this, if you want to get going on one of these missions for human exploration of Mars in 2039, you kind of got to get going right away to make all of this work in a way that you'd have the necessary infrastructure in place on the ground for testing, the necessary infrastructure in place on Mars for receipt of humans some number of years later, and then the necessary test systems completed for the eventual development of a human-capable launch or a human-capable spacecraft system that you would begin building roughly a decade from now. If instead you didn't want to do nuclear thermal propulsion because you wanted to go to even higher ISP, even higher fuel efficiency, you could use what's called nuclear electric propulsion. Now, this is very different in terms of the propellant that's used. In this case, what you're doing is you're using a nuclear reactor core to actually produce electricity. A lot of electricity, megawatts of electricity. That amount of electricity is actually then being used to accelerate a noble gas, something like xenon or xenon doped with helium. And the acceleration of that xenon gas, which you can store at very high pressure, so a large volume of xenon or xenon doped, helium doped xenon, you can store a lot of that and you can get 3 to 4 times the fuel efficiency that you can get out of a nuclear thermal propulsion system. So what that means is you would operate this for a much longer period of time. It would fire for a much longer period of time and get you to a much higher terminal velocity. So you might operate this the entire transit from Earth orbit to Mars orbit, and you actually use it to decelerate as well. So firing this for 200 days, where a nuclear thermal propulsion system, you're going to fire it for 10 to 15 minutes and then coast and then flip the system around and decelerate for 10 to 15 minutes so that you get captured into Mars orbit. In the nuclear electric case, you would actually fire the engine the entire time. So you're constantly accelerating over a long time so you can reach a much higher velocity, much more efficient use of energy in this case. More complex, right? You've got a nuclear reactor that's now generating large power. That power has to be transferred from heat into electricity. That electricity then has to be used with large electric propulsion systems to create the thrust, using what's called the Hall effect to accelerate that working fluid, the propellant, the xenon gas. So what's shown here on the left is what the National Academy recommended if NASA chose to use nuclear electric. A lot of additional development required, but a much more efficient vehicle if it were to be successful. So I think with that, I've left myself about 10 minutes, Scott, for questions, if there are any questions. And I appreciate the opportunity to introduce the intern group to nuclear propulsion.
Jonathan, this is Scott. No, we thank you. That was just a fascinating presentation. Thank you very much. I know our interns enjoyed it. We have, like I said, we have interns that are actually at the Savannah River site participating, but we also have people from across the country. You had a very good turnout rate. People from Alabama, Austin, Texas, Southern California, Northern California. So it was well received. Jonathan, I'm going to ask you the first question. And this is what I want to get from each of the presenters. If you were going to provide a single piece of advice for our interns, what would you share with them in a manner in which they could really make their careers the most successful and rewarding possible?
Oh, well, that's actually not an easy question to answer. I wouldn't put it at any one thing. I'd say there are a couple of things that I have found that have really offered me the opportunity to make the most out of my career. The first is the diversity of my education. I have bachelor's degrees in physics and math, but I have minors in political science and computer science. And kind of having a background in those different things has allowed me a lot of different opportunities that I may not have had if I only had a singular focus as an undergraduate. But a different approach to that was I also had an undergraduate professor that sponsored me doing intern programs. And those intern programs really offered me a lot of opportunity to know what I wanted to do. And so the diversity of education and experience, the combination of those things early in my career, I found to be of pretty significant value. I also think it's underrated, often underrated, the value of a good mentor. And I've had the benefit, the distinction of having several high value to me personally mentors, both professionally and personally in my life. And whether those are religious or professional or personal or whatever they can be, if you find a strong positive mentor, someone that you can discuss without retribution the types of challenges and issues that you're facing, not only can that provide you with the type of emotional stability that can allow you to power through some of the setbacks that you'll face, it'll also provide you some of the guidance and wisdom that people of positive influence can have and share with you. So those two things I think are pretty important. And the last thing I would say is I've had 3 careers now. I had a career as a rocket scientist, as a heliophysicist within NASA, which is a great career for me. I had a career as my own startup. I started a machine learning company and did that and was successful at that. And now, chief technology officer for a nuclear manufacturing company. So willingness to take chances and risks and know that the education and the backing of your family or your belief in yourself, those types of things will put you in a position to try lots of interesting things and hopefully have a productive and rewarding career.
Now, Jonathan, that was really good advice. Thank you for that. So Leslie, let's open up to the questions and let's start with the interns at the Savannah Riverside. So Leslie, why don't you lead this because I can't see.
We don't have any questions yet in the room, but if anybody had questions that either dialed in through WebEx, if you could use your raise your hand function, so maybe we aren't talking over each other, I can call you out. Or if you dialed in with the phone, just shout it out. Maybe. Holly Ashley?
Yes, that was excellent, Jonathan. I really enjoyed hearing you speak about all of the different things you're doing. But one of the questions I had as you were going through the slides is, what is the physical size of the nuclear thermal propulsion system? You had it up on your previous slides, and I just wondered, how many feet long is it, width around, that sort of stuff?
Oh, Holly, that's a great question. And maybe the answer will surprise you. Depending on the amount of thrust that you want, you might have something that's about 1.25 meters, so 1.25 meters in diameter for a smaller thrust system, and only about 2 meters in diameter for the highest thrust system that we've been looking at, and about and about somewhere between 1.25 meters and 2 meters in diameter, and something of the order about 2.5 meters, maybe up to 4 meters in length. That's the reactor core. Now you're going to add another 0.75 meters to 1 meter for the outer shielding reactivity control system. So something, let's say something on the order of about 4 meters in diameter, and something of the order when you put the aft skirt and the rocket nozzle and the turbo machinery that sits on the fuel tank side, so toward the spacecraft, that total length might get you something on the order of 8 meters in total length, depending on a couple of different variables. So say 4 meters in diameter and somewhere between 8 and 10 meters in length is generally what people are talking about for the propulsion system. Now, the Space Launch System, the heavy launch vehicle that NASA is developing, has a fairing that's more than accommodating. More often than not, people talk about a 7-meter fairing or a 10-meter fairing. For those systems, the big launch vehicle for SpaceX is similar in size. They can carry 100 metric tons into space. This propulsion system that we're talking about, when fully integrated as a completed propulsion element, is going to be somewhere on the order of 30,000 or 30 tons. So there's more than enough lift capacity and volume in current fairings to take the propulsion system up, but then the tank and the spacecraft are actually larger than the propulsion element when you look at the fully integrated vehicle. But there you go. 4 meters in diameter, 10 meters or so in length.
I figured it was going to be smaller than what they're using now.
Now, that's still a fairly substantial amount of power, and it's an interesting reason why. Just very quickly, I'll answer that question. Why? As you're burning the reactor fuel, as you're actually creating the nuclear reaction, you're only going to use 4 to 10% of the uranium-235 that's in there. But you're also going to build up xenon and other things that are going to be poisons to the operation of the reactor, and you want to be able to transfer a lot of that thermal energy into the working fluid. So you have to size those things accordingly. And that drives diameter, and the use of the moderator also drives diameter. So there's a variety of different things that add to the diameter and to the length to make sure that you get the right energy into the working fluid, into the hydrogen.
Thank you.
Absolutely.
So Leslie, do we have any? Oh, yes, we have more questions. Go ahead, Leslie.
We've got a question in the room, so we're trying to work out our technology here.
Okay, bear with me because I don't have a background in this, but is there any nuclear fallout from the propulsion? And if so, how do you control for it?
So, good question. The nuclear reactor is not operated until it's in orbit, right? So when it's sitting on the launch vehicle, it's just or on the launch pad, it's just a big block of uranium metal, so not radioactive as yet. There's no nuclear inventory. There's no nuclear reactions to date when it's being launched. So there's no source of radiation on the launch pad. Now, when it gets into space and you operate it, you are going to create nuclear inventory inside the reactor core during the operation of the reactor. So you do have to shield for it to protect humans or cargo that are going to be in proximity to it. But the actual radiation environment in space, it far exceeds the radiation impacts of the reactor core, especially when the reactor is shut back off and you're not operating it in the case of a nuclear thermal propulsion system. So there's no large concentration of reactor byproducts through the operation of the reactor during the operation of the reactor. In terms of fallout, what people mostly mean for fallout is the reactivity products get out into the environment and can do deleterious things like expose people to radiation or toxic materials. In the case of this system, all the reactivity products are contained within the core, and so they don't get out and do anything nefarious. And the hydrogen exists for such a short period of time, persists for such a short period of time in the reactor itself. It's not too much of it's being converted into other things, other isotopes of hydrogen like tritium. So it's passing through relatively quickly, and then once it reaches space, space is mostly a vacuum, so it gets dissipated, and no significant impact there. So long answer I just gave, and the short answer is not much.
All right, we have time for one more question.
I saw a hand raised by David Kelly.
Yeah, thank you. So I know you touched on this a bit, but I was just wondering what factors specifically drive the higher specific impulse for NTP compared to chemical combustion?
Thanks for the question, David. The ISP is directly proportional to the maximum temperature of the working fluid, in this case, hydrogen. So the higher the temperature of the hydrogen, the higher the specific impulse. So if you're right around 2800 Kelvin, the specific impulse is about 900 seconds. So if you drop down to 2500 Kelvin, you're about 725 seconds. And if you get above 3000, you're above 3000 Kelvin, you're above 1000 seconds of ISP.
Yeah, thank you. So what for chemical, what is that temperature differential compared to nuclear?
Okay. So for a chemical combustion system like liquid oxygen, methane, or liquid oxygen hydrogen, it's somewhere between 375 seconds of ISP and 450 seconds of ISP. But the outlet temperatures are not substantially different. The difference here is because you're using hydrogen as the propellant. Hydrogen has such a lower molecular weight to those combustion fuels, you get a higher ISP out of it as a consequence. And the operating temperature of the hydrogen is, since you're operating at hydrogen with a lower molecular weight, you're getting more fuel efficiency out of it, so higher ISP. And in the case of the propellants for chemical engines, it's higher molecular weight and to some degree a lower temperature. The outlet temperatures for the shuttle main, the SSME, the Space Shuttle Main Engine (SSMEs) was roughly 2200 Kelvin, I believe. So lower operating temperature and higher molecular weight, and thus lower specific impulse.
Awesome. Thank you very much.
Sure thing.
All right, with that, Jonathan, thank you very much. Again, that was just a fascinating presentation. So we'll conclude the second of our 5 presentations now. But next week, we'll have Mr. Bill Dornsife. He was a nuclear engineer for the state of Pennsylvania at the time that the accident at 3 Mile Island actually happened. And he'll be sharing his experience with you guys with that next week. But I wanted to thank all the participants, both at the Savannah River site as well as those that dialed in. I hope you guys found that as fascinating as me. And again, thanks so much, Jonathan. And with that, we'll conclude the lecture today.
Take care, everyone. Thank you.
Take care.